Well, thank you very much. It's a great pleasure to be here, and I'd like to thank the American Association of Physics Teachers for this great honor. I've been inspired by a number of the past recipients of this award, so I'll try to say something that's equally inspiring this morning by describing some of the influences that have led me to where I am today. I'll also talk about some of the teachers who were very innovative and, like you, really were very encouraging to their students and the big effect that had on me. I've been called many names in my life, I mean many professional names, and among those are optical physicist, senior engineer, manager of science education, consultant in science education, consultant in optical engineering, and now observatory scientist. But the name I value the most is really science teacher, and I'm sure most of you feel the same way, because that's a very special name indeed, and to be honored by the Milliken Award is high praise indeed. I actually will be talking a lot about tools for teaching, tools for research, and part of that motivation is that, for example, one of my physics teacher in high school went away for a summer to Argonne National Lab and brought back a whole bunch of neat experiments on radioactivity and other things. And suddenly we had a full-fledged opportunity to conduct experiments to actually look at things like the Milliken electron charge experiment. I don't think we used oil drops, it was latex spheres. And my teacher, Gary Fornander, then pulled all that into the lab and gave us a fantastic opportunity to actually do these experiments. And that's the kind of thing I know that you all are trying hard to do, to give that really authentic, fundamental experience in physics and physics research, physics process, science process. And that's what has inspired me, is this ability to interact with the phenomena. So I have to really thank everyone, all of my colleagues, all of the partners on different projects. It isn't something I've done alone by any means. Every single thing good I've done has been a collaboration with professional organizations, with people like you who have really helped me learn about things. I've listed just a few of the partners from different projects, some of the logos. They say a project is never real until it has a logo, so with that in mind, these are some of the logos. And I'd like to particularly thank the National Science Foundation. That's not just because I work for a facility that is sponsored by the National Science Foundation through the nonprofit group Association of Universities for Research in Astronomy, but also because NSF really has been on the cutting edge of teaching and research. And I don't think we realize how lucky we are in this country to have an NSF who can develop these new curricular materials, create these resources for teachers, work on improving teacher professional development, creating science center exhibits and so on, as well as the fundamental research that we know it does. That's a very lucky situation indeed, and as I travel around the world, I realize more and more how lucky we are to have the ability to start these experiments. Well, what I'm going to talk about today are what I call hard problems. Some people call them wicked problems. I don't particularly like that definition. These are just hard problems. They're not impossible problems to solve. And I wanted to try to give you a little bit of a perspective on how we might approach some of these hard problems and teach to help our students address these hard problems of the future, which are complicated problems that actually our future does depend on this. So we need to make sure that they're well trained in this area. What I call a hard problem is things that the problem has a lot of framing issues. You don't really know what the problem is. It's ill-structured. You can define it any way you want. You might define it as a small thing or a big thing. If you start asking around to the people who care about this problem, you might actually get very different definitions of what the problem is or their perspective on how it might be solved. The constraints may be changing. So if you're trying to design an educational program to work in schools, or you're trying to create a new program for your community college, it might, by the time you get somewhere or get a pretty good idea of what you want to do, it might be very different. You might be under a different financial situation. You might have a different student population. Your own personal situation might have changed. And the problem doesn't get solved in a definitive way. It's not one and out, or you can't just say, I'm done, it's all over. The problem always keeps on going in a new form, and your solution may have to spin a new form as well. But I want to remind you that the solution of these hard problems is actually very, very critical. And Milliken had a hard problem. He was trying to find the fundamental unit of charge, and it was not so simple. When I look through the archives at Caltech for Milliken, you find out, first of all, he worked a lot at night. Maybe that was because he needed a quiet environment or less vibration or something like that. Or maybe he was just a night person. But oftentimes, when you look through his notes, you'll find out that he'll scribble things on the paper that basically say, you know, this is really frustrating, or can't do this, or this doesn't work. And but occasionally you'll find something that says, what I think on the right part there says beauty. Maybe it says publish underneath it. I can't quite read it. But you'll see this basic, number one, the lesson I take away is science is not all concise. There's a bit of sloppiness to it all. It's a lot of experimentation. It's a lot of prototyping. And when you look through his notes, you see that you probably would have given an F on his lab notebook if this was turned into you. You would have said, wait a minute, look at all those scribbles, look at all those little things. But he tried this experiment many times before he succeeded, and there's a lot of iteration in the process. So that's something to keep in mind when you see a really scrawly lab notebook coming at your way, or results of an experiment. Maybe you have the future Milliken in front of you, but maybe give a little bit of encouragement, because the hard problems don't always lend themselves to very neat columns, and they often have a lot of experimentation and prototyping along the way. So here's the one that says beauty, and then I think it might say publish underneath it. So that's kind of exciting that he did these scribbles using different colors. You're going to see a big emphasis in this talk on tools, and obviously their tools, scientific tools, are at the frontier of our knowledge, and in astronomy, we have evolved a lot with our tools, with our telescopes, with our detectors, with our numerical calculations. Whereas 15 or 20 years ago, astronomers would say, I'm going to the telescope for a couple nights to measure the rotation curves of 5 or 10 or 15 galaxies. Now they're talking like, our team is going to spend the next 3 or 4 years working with a lot of other people along the high-energy physics type world where there's big teams, and we're going to measure the redshifts of 350 million galaxies on Kitt Peak. So we're moving into a totally different paradigm for science and for big teams and for big projects that will provide data to the whole community. The Large Synoptic Survey Telescope is one of those as well. So I'm going to talk about ill-structured problem solving, which is the hard problems, the complex problems, the optimization problems. I'm going to kind of argue that we need to practice on these problems, as there's a myriad of skills involved in solving these problems. And I'm going to also argue that we shouldn't necessarily spend our efforts to sort of dissect all those skills and figure out all the different ways that students should do certain kind of mini skills to work on these. I'm not trying to design a calisthenic program to exercise these different skills and then put them all together at the end to solve the problems, but rather arguing that we ought to be exposing our students to very hard, authentic problems early, and let's see if they can get some skills or get some improvement along the way, and then maybe they'll need to go back and learn some basic skills, or they'll realize they need to learn a new form of numerical analysis, or they have to up their experimentation technique, or they have to go solve a certain mathematical physics equation in a better way. But they'll realize where their limitations are, and they'll come back to that in the service of this larger problem. And I also want to argue that the tools are absolutely critical. And I had a high school teacher, Elmer Nelson, who would say something like, the person with the longest pole picks the most persimmons. Now, that's a tongue twister, but he would say that, and he'd put on his Zen face and keep saying that, and you say, well, what does it mean? And he wouldn't explain anything, of course. He would just repeat it again very slowly. And so I thought it'd be very important to show a picture of the persimmon pickers and think about the tools that we have to address these complex problems. Now, one generation's hard problem may be the next generation's easy problem. So in the early 1900s, we knew there was a bright star called Alpha Centauri. And this, in the lower left, is a very overexposed picture of Alpha Centauri and its neighborhood. So we thought that was probably the closest star to us. But people who were interested in stars knew that stars usually come in doubles or triples or quadruples. That was pretty well known. So does Alpha Centauri have a companion? Well, maybe it's in this picture. Which one do you want to look at? How do you want to probe this problem? You want to measure something about every one of those little dots in the picture and see what it is? Well, okay, you find a technique. You find a better way to do it. You know that Alpha Centauri moves through space, has a certain velocity, a proper motion, and you look for stars that are moving about that same rate. And so 1915, I think it was 1915, yeah, using proper motion and parallax, we found out that there is a little star that is a companion to Alpha Centauri. It's called Proxima Centauri because it turned out to be even closer to us than Alpha Centauri. That little cross is where they found Proxima Centauri with some effort. And so brute force may not have been the answer, but something a little more creative was. We don't even know if Proxima Centauri is part of the system because it takes about 500,000 years potentially to go around each other, these two stars, or three stars actually, to go around each other. But we think it might be related to the Alpha Centauri system, but it is our closest star. So you'll see in my talk, my philosophy has always been, how can we motivate students to want to go solve some hard problems and sort of learn the skills along the way. So this is kind of the theme. Give them something interesting to do, and then they'll realize that they don't know how to do it, and then they'll want to learn some particular skill along the way. So when I was trying to teach a program on image processing for teachers, instead of the usual way of, okay, here's all the tools in NIH Image or ImageJ now, my motivation was this: let's create a scenario. So my scenario was a plane had crashed in the Grand Canyon, and we needed to figure out exactly what caused the crash. So we had some old inspection reports from the people who had repaired the plane last, and they had x-rays of different parts of the plane. I actually got x-rays from the Lockheed plant near Tucson. And then they looked for a little crack, and they had to use all their image processing tools to find the little crack and see if there really was a problem. So it's ill-structured. The plane crashed. We don't know if there's a problem. We don't know why it crashed, but we have a little bit of evidence, and we can go investigate with that evidence and use our special tools of image processing to see if we can find something really exciting about it. So that's been my philosophy all along, is to try to create that motivational situation. I was also influenced as a child by the book by Victor Weisskopf called Knowledge and Wonder. In fact, this was a book that my mother asked the science teacher, hey, is there anything that Steve could read? And the teacher recommended this science study series, and I read 5 or 6 or 7 or 8 books in this series. Still a tremendous series. And this quotation from Bacon, I think, really epitomized my philosophy from an early age, which was that knowledge and wonder, which is the seed of knowledge, is an impression of pleasure in itself. So knowledge and wonder, pleasure. The concept was that you could wonder at the natural world, you could get inspiration, you could get aesthetic enjoyment, and that may propel you along towards further knowledge. That was very influential, and it's a great book if you haven't looked at it. But along the way, I also saw these kind of images in my children's books that I think captured my imagination as well. The one on the baseball one is the idea from, I think it was a book called Our Friend the Atom. It was the idea that if you took away the space in an atom, you could take all the battleships in the world, and it would be the size of a baseball if you compressed it all together. I don't know if the physics is quite right or not, but that was the visual impression. And it also had a book on the moon, and it was wonderful. It had drawings and paintings, and it had things like the Great Wall on the lower left. And it had also a picture of the Earth very close to the moon just after the formation of the Earth and moon. And of course, it didn't quite know which theory of the formation of the moon would be correct, but it did describe them all. And those pictures made a tremendous impression on me, and I thought about that. I was very fascinated by the concept of an early history of the Earth-Moon system, the moon being close to the Earth. And really, I won't get into it in this talk, but you know, about 15 or 20 years later, guess what? I found myself working with a friend of mine, colleague, Peter Kahn, and we started working as undergraduates at Rice on a project to try to figure out if we could solve the Earth-Moon history problem using fossils, using fossil rhythms, biological rhythms in fossil shells, and looking for modern analogs such as the chambered nautilus and fossil nautiloids. And we could somehow chart off the history of the Earth-Moon system from way, way back and find that time when the Moon and Earth were very close together. And we worked on that as undergraduates. I worked on it when I was teaching junior high school, and we ultimately ended up publishing a very interesting hypothesis that said we think that nautiloids and their growth rhythms can capture throughout history the distance from the Earth to the Moon, changes in the Earth's rotation rate, and the changes in the lunar orbit. And that was published. So who would have known that that would have happened? Well, actually, it's not so difficult to think about that. When you have a strong visual impression or a strong visual image, it can carry forth in very, very powerful ways. I became fascinated by the beauty of spiral galaxies, and guess what? I have a PhD in spiral galaxies. I could have chosen nebula, I could have chosen a lot of things, but I ended up being very intrigued by spiral galaxies, particularly early type galaxies. And guess what? One of the great images in my mind is the Sombrero Galaxy, which I think is one of the most beautiful images in astronomy, and I specialized in what are called SA galaxies, early type galaxies. So these things are not so unpredictable after all, and you need to be appreciative of how your students can be captured by this kind of imagery. The fascination with physics and physical phenomena can go in every direction. From the aurora, my advisor as an undergraduate was an auroral physicist, or one of my advisors, and I was always fascinated by that, and space physics always held a great fascination. So there's a lot of power to that. Here's another image. This is from the work of Fritz Goro, and tremendous scientific photographer. This picture, I think, could stimulate a whole career in optical engineering, and in fact, it sort of did for me as well. This is just how light goes through lenses. These were old lenses with no anti-reflection coatings, and light scatters around, and guess what? A bunch of years later, what's my specialty? Stray light and optical systems. So these things carry on for a long, long time. My fascination with light, with spectra, with the control of light is carried over to trying to understand how LED streetlights are going to affect our lives in the future. But I think there's sort of an ontological principle here. You can go out and buy a little tiny spectrometer for a few dollars, and you're be able to conduct an experiment that people 100 years ago would have died for, because they didn't have this equipment, they didn't have these tools. And that's where it always is. Science usually progresses along these new tools, whether it's something big and amazing like the LIGO facilities, and actually played a very small, very tiny, tiny role on LIGO, on coatings. So something gets built, it gets refined, it gets engineered a little better, it gets perfected, and then suddenly you realize the universe is not the way you thought it was. The number of black holes isn't the way you thought it might be. So I wanted to now move on to talk about sort of I call it my engineering side. And I was very, very lucky that when I stopped teaching in public schools, I got a job with an aerospace company, and I kind of fell into it. I actually wanted to write a book, and I wasn't very smart about that, because I thought, oh, I'll just take a year off and write a book. But that wasn't quite so easy to do. So then I found myself looking for a job, and ended up working for Martin Marietta Aerospace in Denver. And it was a great group to work with, because I ended up in a small group of people who are the most creative and talented scientists and engineers in the whole 15,000 person group in Denver. And they got all the challenging assignments, the fun assignments. I think we were kind of cordoned off maybe because we were disruptive in some way. So we were kind of kept over there until they needed us, and we would do internal research and development things. And then whenever they needed to solve a multi-million-dollar problem, they'd pull us out of the lab and say, hey, okay, we got a big problem here for you to work on. So I think that was great, and I was very lucky to have, as office mates, just as an illustration, my little cubbyhole had me. It also had a guy who was really good engineer from Colorado School of Mines, had a woman who was a neurophysiologist who now has turned to the aerospace industry and later became director of a lot of launch services for the company, had a chemist who did some fantastic work. And it also had a guy who was the world's greatest expert on high vacuum. And he became my very good friend and colleague, and we invented a lot of things together. But he was a good example. So he would be doing off in the lab, working on things. And then a couple times a year, they'd come to him and say, we have a problem with the Mars descent probe. We don't think it'll work, basically. And the problem has to do with vacuum and windows and seals. And look, it's not going to work. And our contribution to the NASA mission is going to be in jeopardy. So can you help us? So he would go off and study the issue and come back in a few weeks, and he'd usually solve the problem in some unique and very creative way. And then he would be asking me like, well, what do I do for time cards? I don't have any time cards. I don't know what to charge my time to because my research and development project's about over it. I just saved the company a couple $1 million, but it only took me a week to solve that problem. What am I, can I put down 2 weeks? Can I be ethical about it and put down my time card for 2 weeks? Otherwise, I got to scramble around and find somebody else's problem to solve in the next week. Can't do this every week. So he would save the company millions of dollars, and later he was named the inventor of the year for the company for some of his special inventions on leak equipment and so on. So one day I was reading the results of oops, sorry. I was reading the results of a new mission that was had flown called the Infrared Astronomy Satellite. And the Infrared Astronomy Satellite had a little problem. It did some really fantastic things. But I read that the coatings really didn't quite work at the longest infrared wavelengths. They were trying to block the sunlight, the moonlight, the earth shine. They were trying to block everything from affecting the detectors. And it really didn't work. And they were getting ready to build a new shuttle experiment called the Shuttle Infrared Telescope Facility, SIRTIF. And they said, we got a problem here. We really want the best performance at long infrared wavelengths, say 500 microns. But our coatings seem to fall apart at 5 microns or 10 microns or something like that. So I thought, well, this is a great opportunity for me. Now, it isn't that they came to me with this problem and said, hey, Steve, solve this problem. Actually, it was a little bit different than that. I'd gone to this really interesting group of the company, and when I first got there, they said, hey, why don't you pick one of these projects to work on? They gave me three things to look at. So I read them over, and I said, 2 of these are going to be really hard. I'm going to flop immediately on these 2 projects. I don't know enough about these areas, and I'm not sure I can learn fast enough. So I said, project number 3 is the one I want to work on. After great deliberation, because I thought, well, as soon as they find out I can't work on project 1 and project 2, they're going to kick me out of this company. I just come from teaching high school, and my expertise was in nautiloids, secular evolution of the Earth-Moon system. So I said, oh, I want to do project number 3. So they said, well, I'm sorry, project number 3 is already taken. Well, fortunately, we had a Christmas break then, so I had a little time off to think about it, and they had a little time off to think about it. When I came back, they said, okay, how about you work on this interesting project on inflatable structures in space? So they gave me the project to think about very large football field-sized inflatable radio antennas, and they wanted to know about the space environment. What were the effects of the space environment on these different things. So I did all the usual physics things, talked about the spacecraft charging and how different parts could get a charge and they'd start to warp. And I talked about micrometeoroids, and I talked about the effect of ultraviolet light on these things, and so on and so on. And I wrote a whole scholarly paper on this, which they liked very much. So then I thought, okay, that's great. I've proven myself. But what do I do now? Well, I heard about this project, and I thought, well, gee, this can't be too hard. I knew pretty well that what the answer had to be, because I knew the coatings were starting to look very, very smooth when you subjected them to long wavelength infrared light. So if they were good, interesting, absorptive coatings in the visible or ultraviolet, and we had one of the best coatings ever made at that time at Martin, called Martin Black. So I thought, what can I do to Martin Black to make it a really good infrared coating? Because it had obviously not worked super well on this infrared satellite. So we didn't have anything better. So I thought, okay, I can figure it out. All I got to do is make it about 10 times better. That would be very impressive, right? If I made something 10 times better, I thought, that's easy, I can do it. And the answer was, I think I'll just make it a lot rougher. So that was my idea was, okay, I'll just create a really rough coating, and that way it'll be rough to infrared light, it'll be cavitous to visible light. So I thought about all these different kinds of rough coatings that I knew about, and I started thinking about the space environment, because that was what I'd been specializing in. I thought about coatings that stick up off of a surface. I thought about coatings that were holes in a surface. I was really kind of thinking about the stacked razor blades that I learned about in my introductory physics class. We all know that a very black light trap can be stacked razor blades. You just bounce the light deeper and deeper into the stack. And I knew about Wood's horns and all that. And so I thought, okay, I'll just find a way to make holes in the surface or protuberances, and we'll find a way. I knew if I could get things to bounce around a few more times, it'd be great. So I started thinking about BRDFs, which are bidirectional reflectance distribution function. I had to sort of go out and figure out a way to characterize surfaces. So actually, we started designing and building probably the world's first really nice scatterometer, where you can shine light at a surface. So so BRDFs are a fancy equation, but really what it means is I shine light at a surface from every single potential angle, and I notice how the light is scattered, reflected, or absorbed at every potential angle. So I shine light from a hemisphere, every angle, and I look and see what the effect is, how much is reflected at every angle in that hemisphere. And then I try to make it so it scatters over the whole hemisphere. That'll make it a lot blacker coating, because after all, in a telescope system, you're trying to send the light in certain directions and keep it from going other directions. So I had a great time thinking about absorbing surfaces and how to modify this Martin Black surface to make it infra-black. So this was an anodized surface. So the idea was to create fractal type surfaces where you could put big structures, and then on top of those big structures, some medium structures, and on top of those medium structures, some little structures, and maybe somewhere along the way you can find some infrared absorbing chemicals or materials that would absorb the light in a different way. So you're using a whole repertoire of different techniques to do that. So that was what got me very excited. On the meanwhile, I was also working on cryogenic motors in space, ways to make a motor shrink to the right size at liquid helium temperature, take a regular kind of motor, stepper motor for a spectrometer, and make it kind of shrink to the right size so it would work at liquid helium but be kind of sloppy at room temperature. So that was a fun project. It was very practical. Everything shrinks at a different rate. You can't always tell what's in the motor. You have to kind of experimentally make it shrink to the right thing. So I did that and worked on that, but I really got excited about these infrared absorbing surfaces. This particular surface, infra-black, was actually highly absorbing from the vacuum ultraviolet, from perhaps even 1,000 angstroms up to about 500 microns. So that was a real coup. And it was actually used later to make the best measurement ever of the Stefan-Boltzmann constant by the National Physical Lab in England. So it made a great blackbody surface. So somewhere along the way, got fascinated with blackbody surfaces. Well, the next step would, of course, to put this surface in a telescope and figure out how much better. Remember I said I wanted to make it 10 times better, maybe 10 times better on the surface, but if you put it in a telescope, you can actually make it 10,000 times better because you have lots of bounces, and if you make one surface better and you can control the bounces and put them in different directions, you can end up with something 10,000 times better. So we predicted that it would be 10,000 times better in this telescope. And unfortunately, the telescope, the shuttle infrared telescope, later got delayed. It wasn't a shuttle experiment. It later became the Spitzer Space Telescope, and some of the tricks we came up with were used. So another thing along the way was the idea of making telescopes better, particularly for looking at faint objects, for example, planets around other stars. So we started looking at how we could model telescopes, change the coatings, but more importantly, look out for the stray light and make it go. So we found ways to model complex telescope systems for stray light. We even modeled the floor of the telescope structure, the linoleum. We actually had to take a piece of linoleum, and we didn't really have money to do a BRDF measurement on it, but we actually looked at it. We got a couple of our friends who are good at BRDFs, and we looked at it and said, I think the BRDF is about this. So we would kind of shine lasers on it, and we'd look at it and look at how it behaved at glancing incidents, grazing incidents, and then we actually sort of put in a BRDF number. So we did this for quite a number of different telescopes, including the Apache Point Observatory, the Sloan Digital Sky Survey. Some variation of this was done by some of my colleagues for Hubble, for all of the different telescopes now. So it's now a standard part of the whole practice to model these things. And really the field of seeing very faint objects next to bright stars is going to be very much transformed by how well you do the stray light analysis and how well you think about these kinds of things. Okay, that was great. Those were I'll call them the rocket science days. Those were highly challenging. We had a lot of fun. We applied this to things like SOFIA airplane, the infrared airborne observatory. We got to do this on a lot of neat projects, and we had kind of a neat role because we could always make things better and fix things up. And that was pretty exciting. So at a later point in my career, I started thinking a little harder about how to improve things from an educational perspective. And I realized very quickly that education or educational improvement or educational system improvement really isn't rocket science, right? Rocket science is sending rockets up. The company I worked for built the Titan missiles and sent a lot of things into space. That was rocket science. You could go to the factory and you see a big rocket sitting there in front of you. What about education? Well, I think it was Pinky Nelson who said this. He said, it's not rocket science. It's much harder than rocket science. Okay. And I agree with that. Now, why would education be harder than rocket science? Well, it's complex situations. It's these hard problems, but maybe even more complex. There's feedback loops. There's impedance mismatches between the stakeholders and partners. You can't even agree on the problem or what the solution is. If you find a solution, you can't distribute the solution. So it depends on how narrowly you define the problem. Maybe you solve it locally. Now you're thinking, this is a great model for the whole country. How do you do that? How do you get that out there to the rest of the country or the rest of the world? Very, very tough thing to do. Well, I was lucky enough to join up with a really creative group as a consultant at the NASA Classroom of the Future in West Virginia. They're a group that was kind of the research and development arm of NASA education. Their job was to create the educational experiences for 5, 10, 15, 20 years from now. And we started creating a product called Astronomy Village. And the idea was that we would create an immersive, almost gaming experience where students would come to the Astronomy Village, which was modeled off of Kitt Peak, and they would go to different buildings and do different things, and they would pursue a research project all inside the computer. The neat thing was that we incorporated several firsts. We had Netscape. I think it was the first real program of this sort that actually let you go off to the web. And it also had simulated email. Email was not really used in general except by scientists. But we created simulated email. So when they got into the Astronomy Village, first thing they got was a message from the director of the Astronomy Village. And she basically said, glad you're here, get to work, get to work. And you got a big job ahead of you, get going. So she gave some guidance and encouragement, and the students went off and they got to they kind of interviewed all the scientists at the Astronomy Village, and they actually got a chance to sort of pick a project. So every scientist got a chance to pitch a project to them. You want to search for a supernova with our team, or do you want to look for Earth-crossing asteroids and save the Earth, or do you want to help us design the next observatory of the future? So they got to choose a project, and then they got to do various thought experiments, hands-on experiments, library research, observing with our mock telescope you saw in the previous slide, and they got to actually pursue a project. And the end of the project was a press conference. They actually gave a press conference on their results, and of course there are always a few snarky press questions. That was part of the whole experience, was to get the snarky press questions. So that was the immersive experience that we thought was preparing students to understand the process of astronomy and pursue a more authentic investigation. Well, as you can see from the graphics there, that was a fairly early attempt. We, under National Science Foundation funding, we created another project which was on exploring the solar system. So this was more middle school now. And the model was, you're on Mauna Kea now, and you get to go all around the Earth on your different stations. You get to look at interplanetary probes and basically pursue only two questions. One was searching for life in the solar system. So you got to go on deep sea submersibles and see what it was that perhaps created life at deep sea vents. And try to understand what it is that life needs. So you could go looking around the solar system for life. And then the other thing you got to do was to try to figure out Pluto. And we had no idea what Pluto was like. We didn't even have a mission heading towards Pluto at that time. But the idea was that you would do comparative planetology, and you would start understanding what's in the solar system, and maybe you could figure out what Pluto should be like or could be like. And that was the same thing. The same model was in place. You went to a conference room. Your mentor, the astronomer, she would say, okay, you've joined the Pluto project. Here's what we got to do. Here's some of the high points. Here's the things we got to handle right away. And you had a choice. So there's a lot of learner control in all of these things. And that's a key issue in all the projects I've been involved with, is you have to give people opportunities, you have to give them control, you have to give them the chance to move in different directions or be a part of a team with different roles. So they got to solve the mystery of Pluto. I only wish this project could have, it was all published and distributed, but I only wish it could have kept on going and been revised just in time for the Pluto flyby. I also worked with groups that created even more immersive projects. This was a project from Mission Research Corporation called Apollo 2000. We actually created an interactive environment where you could go into, for example, Galileo's laboratory or Galileo's house, and you could literally be the sidekick to Galileo. And you could be doing things with Galileo or suggesting things. And we created a way to do that, where you could participate with a scientist. And this model actually works great for poetry, social studies, history, and so on. Unfortunately, the project didn't go super duper far, but we had some beautiful ideas here. Okay, so those were some of my interesting projects with multimedia and trying to figure out exactly how we could create an immersive, science-oriented environment. Obviously, it's better to just put the students right in a lab and do things directly. That's what a lot of you are doing, putting them as an apprentice or as part of a larger project. But I was moving on in a different direction. I was chosen to be the project lead for the International Year of Astronomy 2009 for the United States. And I was also the head of the Telescope Kits and Optics Challenges Working Group. So we kept having meetings and talking worldwide about the idea that wouldn't it be great if students could have this really fantastic experience looking through a telescope that we had all had as astronomy buffs. So we thought, what if everybody could see the rings of Saturn? Wouldn't that be fantastic? And everybody agreed that was great, but we couldn't agree much beyond that. So we had lots of ideas. Well, should we have a real cheap telescope? Should we have a real fancy one? What do we do? So we had a couple meetings, and then it kind of disbanded because we couldn't even agree on whether the telescope needed a mount, whether it should be cheap, whether it should be expensive, how are we going to distribute it? So we stopped. We just thought, okay, that's a great idea, but what are we going to do with it? Well, I'd been part of another project called Hands-on Optics, and I'd been the project director of that. We'd actually created a unit on telescopes and image formation, and we'd actually used the Project STAR telescopes developed at Harvard, and they were these cardboard telescopes, and they were wonderful for teaching about optics, but not necessarily good astronomical telescopes. Well, we built thousands of those as part of this project that went to tens of thousands of middle school kids across the country. So we'd kind of had it with the Project STAR telescopes. We liked them, but we knew they couldn't ever be really good astronomy telescopes. So we thought, let's, so first thought, my thought was, let's make the very simple front lens be an achromat. Maybe we could get a better quality telescope and do that. Or let's make the single back lens, the eyepiece lens, maybe we make it a doublet or something fancier. So maybe we could modify this telescope and make it into something astronomical. Well, that didn't really work. We did some modeling. We got the computers out and figured out what it would do, and it kind of worked. But we're still dealing with a cardboard telescope. It had no way to be mounted on a tripod. So then we looked around the world, and we thought, wonder if there's anything out there that we could do. So we went out and bought all the cheap department store telescopes we could find, thinking there must be one we could recommend. There's 30 or 40 of these around. Let's find one of them. If we could just tell people in the world the Kmart telescope was great, or the Target telescope was fantastic, or the Little Mead telescope was great. We could just tell people that here's a good telescope, good enough or almost good enough to see the rings of Saturn. And maybe it's overpriced, and maybe it's not available everywhere, but we could at least make a recommendation to the United States kids. So we bought all these telescopes. We set them up in my hallway. We created this little test target, and if you put it at the right distance, it simulates what Saturn and Jupiter and other things look like, size of the moon. And we started testing these, and we could not find one that we really liked. We found some that were close, but they often had a bad eyepiece. Anyway, they were overpriced. So we thought, okay, that's sad, but too bad. So then we thought, okay, well, let's just design our own telescope. So I brought my friends who had helped me on some of these optics projects. We said, give me some free time. Let's design our own telescope. It has to be real simple, inexpensive, but good quality. In fact, they were the ones who said, look, I got turned on to astronomy at a young age, so whatever you do in this project, it better be good. If you create a bad telescope, we're never going to speak to you again. So of course, I used that later. I said, okay, now you told me that 3 months ago. Now I'm going to make you help me design the good telescope. And they were willing to do it. So they had registered very early on their desire to have a great telescope. So they helped me design a really great telescope, and we were about ready to write a paper about how great our design was and all the spots and how it all worked and all that, and that was great. Then we realized that's really foolish, so we write a paper, we publish it at SPIE or somewhere, and everybody says, boy, Steve and his friends are really great telescope designers. What's that going to do for the average kid in the United States? What's that going to do for the average kid in India or Europe or Australia or China? Nothing. Absolutely nothing. We'll have a nice little design. Maybe some manufacturer will read about it somewhere and think about it. But nothing. Absolutely nothing. So then we thought, well, let's see if we can make something happen. Well, fortunately, my colleagues on the project, Doug Arian from Carthage College, many of you know him, and Rick Feinberg from Sky and Telescope at that time, now with the American Astronomical Society, they're also very can-do people. And Doug brought tremendous expertise in manufacturing into the project, and Rick brought tremendous skills overall. So we said, what if we tried to manufacture this? What if we took the design, found a place to manufacture it, and so on? And they did, and we did. And we ended up with this interesting telescope with lots of parts, and very complicated, very sophisticated, not complicated, compared to this Project STAR telescope. And we had to use stereolithography, rapid prototyping. It would never have gotten off the ground because we actually built a prototype using 3D lithography, and built it, tested it, refined our mistakes, worked on all the fixes, on how things fit together, and we had it in time to show it off at the opening ceremonies for the International Year of Astronomy at UNESCO, and people got pretty darn excited about it. So we tested it every chance we could get. It performed fabulously in an optical sense, and people liked it. This telescope, by the way, was designed designed around usability. It was designed around our research on how kids use telescopes and how people see through telescopes. And it was designed for kids who wear glasses because we thought that there would be one telescope and 20 kids, and you can't refocus it for every kid. You got to have it focused once, and if kids wear glasses or not, they keep them on. So we designed it around a long eye relief, so it could be very usable by kids. And that was another project we had done. We also designed it to be an urban telescope, so it would work in the cities. And in fact, the lower right there is a test we did. That's at DuPont Circle. So I'm picking random people off the street and saying, you want to look through my telescope? At 10 o'clock at night at DuPont Circle in Washington, D.C., we're actually looking past a big street light, doing a stray light test. We're actually looking at Venus. I don't know if you can see it, but Venus is a little dot in the middle of the tree. It's very low on the horizon. So we have a little dot in the middle of the tree, that's Venus. We're looking at Venus through a tree, with a street light, with the buses coming, with people coming off the subway in one of the most brightly lit urban areas we have. That was what we were designing the telescope for. Well, happy to say it was a success. We also wanted a kit so kids could actually see what's inside. And that was a key part of our whole project, was to make it assemblable, and you could assemble it over and over and over again. And then we used some of the principles from our hands-on optics project to make it very durable. In hands-on optics, we took all of our lasers we wanted to use in hands-on optics, and we went to a concrete floor, and we just started dropping lasers on the floor, and whoever survived after multiple drops was the laser we wanted in our kit for hands-on optics. So that was our philosophy of educational development, was drop it till it breaks and then throw it away and find one that didn't break. And the Galileo Scope is in the same variety. We dropped it, we tried to break it, and we reinforced things that broke. And we ended up actually with a really nice telescope kit. It's still available, by the way, at galileoscope.org. So they're still being made. We have over 220,000, I believe, out there. And we'd love for you to buy the 220,001 of it, because it's still a great telescope. It still is a great optical bench. It still has great optics. And you can configure it as a Galilean telescope, so you can reproduce the experiments of Galileo, show why he had a great deal of patience when looking through a Galilean telescope. And you can also configure it as a Keplerian telescope. But the whole idea, well, it's restarting, hopefully restarting. I'll just say that it was a great opportunity to build these telescopes. We're very happy to do that. And the real idea here was to give that experience to kids and adults of this aha moment of seeing Saturn. But the other idea was a subversive idea. It was the idea of reinforcing the notion that Galileo knew very well, that science is fundamentally anti-authoritarian, that science is all about discovering for yourself the phenomena of nature. It's not about accepting what the bigwigs say, and no matter how well respected the person is, or how wise they are, or their reputation, none of that really matters. What really matters is the ability to actually go make the measurement yourself, go find out for yourself what exactly is happening. And that was the fundamental thing that Galileo did, that all scientists do, and that we wanted our students to do. So that was a powerful thing. And give me just a moment to get my thoughts together. Build it yourself, use it yourself, be convinced that you've made measurements that are interesting. And we started a program where we had star parties all across Arizona and other places to use it. We're very happy that the Galileo Scope made it to the White House for both star parties in October 2009 and October 2015. So we're very happy that we could bring it there and show it off and show that a very small telescope has tremendous value in an urban environment. Also was very interested in lighting. Anybody who works for an observatory has to be thinking about city lighting, how cities are growing. and what the effects are going to be on us. So I was very keen on the idea that we need to work very hard on preventing wasted light from going up into the sky, blocking our view of the stars. And my colleague Connie Walker and I have been spending the last 10 or 12 years thinking about lighting and teaching about illumination engineering. We have a project that called Globe at Night, which is a citizen science project on lighting. But our latest project is taking a little different approach. It's problem-based learning. It's taking the idea that the students are going to be living in the city of the future. City of the future may have monorails and levitating cars and space cars. I don't know. It may have a lot of things, but it will probably have very bad lighting unless we do something about it. So no matter how fancy it looks in the future, the lighting probably will be worse, actually, because we now have the ability to light up our cities even more with LED lights. We have the ability to put a spectrum of light that is bluer, which may have severe biological consequences on human beings and other things. So we took the attitude that the students are going to be thrown into solving the problems of the city of the future. The kit we've developed is based on the idea that the mayor is the teacher, the mayor of the town or the mayor of the city of the future is the teacher, and the students have to pursue these 6 different key areas for better lighting. And they basically are told, they have a lot of complaints from the citizens that the mayor is trying to deal with. Like, I'm driving down the road, and I'm an older driver, and the lights are in my eye, and I can't really see anything. Or my neighbor has a light and it's trespassing into my house. I can't sleep at night. So the mayor has to deal with these complaints and come up with a workable plan. And the students have to come up with a workable plan on these fairly complex issues. So we give the students the right amount of materials to try to do some experiments. We give them a lux meter, for example. They try to solve these, to the best of their ability, solve these problems, make recommendations to the mayor, and produce plans. This is a project that we're doing with through the International Astronomical Union, with SPIE, the Optical Society, and the International Dark Sky Association, and the CIE, the International Commission on Illumination. So that was great. That's some of our latest efforts we're making. I wanted to talk right now about just another interesting project as I move towards the end here. That is the idea of science and art, the idea that we might be able to find better ways to connect science and art. Now, why do we care? Well, we do know, for example, that a lot of kids are interested in art. We do know, for example, that art has strong emphasis on visual spatial skills. And we know that most scientists have very strong visual spatial skills. And so if you start creating visual pictures about, okay, consider this thing looks like a tennis ball. Now imagine the tennis ball is fuzzy. Now turn the tennis ball inside out. Those are the kind of things physicists like to do. And artists do the same thing. And we know that a lot of girls are interested in art, but not that many end up in physics or engineering. So we have a project that was very much influenced by this book that I saw many years ago called From Art to Science, 72 objects that illustrate the nature of discovery. So it shows how there's an aesthetic realm to these interesting discovery kind of objects, whether it's a shell with art on it or whether it's the pattern on the metal of a knife or a meteorite. So we started looking into some of the overlaps between art and science, and there's a lot of overlaps between art and science. Some of the techniques are a little different. Some of the end results are a little different. Science obviously relies on putting out a result, making predictions, and trying to get those predictions tested by other people. Art is a more individual endeavor that puts out something and doesn't have to pass the test of predictability or others verifying it. But nonetheless, many of the early phases of both science and art, observation patterns, abstraction, and so on, are common to art and science. So we started a project called Colors of Nature, funded by the National Science Foundation. That's both a research project on science identity formation and also a project to try to understand how we can teach with colors of nature, especially biological colors, pigments, and so on. We have a fairly good emphasis on structural color, iridescence, and thin films, which of course are very much present on butterflies and soap bubbles. But the main point of the project is that we actually centered around design challenges. So again, more authentic, problem, creative, project-based things that students have to take on these design challenges and create something that incorporates these properties of color and light. And in the process, they'll learn some of the basic techniques about this. Thank you. They also use a spectrometer, an ocean optic spectrometer, to check out their fabrics, their colors. And the end result is they actually do a poster session where they create a special costume based on a mythical animal that uses color for survival in some way. And they actually they create a very simple poster, display their costume, and then they have people walking around who talk with them about their posters and sort of reinforce this idea of explaining your work and showing off your work. So I just wanted to conclude with a couple of I'll call them hard problems that I'm very interested in right now, because maybe some of you in the audience would like to team with the National Observatory and think about how we can work together on some of these hard problems. So right now we're thinking a lot about rural science education, particularly in Chile. We've had a grassroots science center spring up near our observatory, which has been a great thing to support. And we've actually created a library with a lot of astronomy books in this little center. And we're very excited about this concept of grassroots science education. I was involved many years ago with something called Enchanted Skies Park, which never got built, but it was a really exciting development in New Mexico to create a big science center on top of a mesa. One of our partners in this kind of rural science education project is municipal and tourist observatories, which are springing up in northern Chile, places where you can have beautiful skies, you can have tourists coming in and wanting to see the southern skies, the southern Milky Way, for example, and they can play a big role in buoying up the economy of these small towns, but they can also be great education partners, and they also have a vested interest in preserving their night sky, so they're great to have in a big ring around our observatory, because it's very important for us to preserve our night skies. So our area now is a dark sky sanctuary. It's the first international dark sky sanctuary, called the Gabriela Mistral International Dark Sky Sanctuary. But to keep that going, we need this ring of tourist observatories around us in these small towns to keep the dark sky going. Another challenge that we're very keen on is how can we use undergraduates both to do outreach and to provide a mentoring function to them. I think you know all about the Little Shop of Physics at Colorado State University is a tremendous model for undergraduates doing outreach. And we have our own model of 5 to 7 students at any given moment doing outreach in our programs. And it's a mentoring program to help them get through school, to achieve whatever professional goals they want, whether it's to get a job or go to grad school. And, but also to save our backs. That's one of the goals. So when we have a lot of lifting to do, we have our students do that, because our staff doesn't have the greatest backs in the world. So we need our younger students to help us move things around, and they help us with outreach, and they do everything that we think they can do better than us, which means anything with students that they can provide a role model. So we work together as a team where we can do educational activities, and they provide a great role model for students. And then finally, we're very keen on teaching about big data. As I mentioned, one of the projects for Kitt Peak is find the redshifts of 350 million galaxies and understand the implications of those redshifts for dark matter and dark energy. Well, where does that fit in with the public? Where does that fit in with students, high school or middle school or college students? We don't know. We're trying to figure that out. And again, any project you want to deliver should be thinking about mobile phones rather than computers. So although I tend to think of this as, well, gee, a big screen would be great because we're going to show all these great things and visualizations, most younger people are thinking, can I see it on my cell phone? So we have to think about the role of mobile phones, both as data displays and also as scientific displays, because people can attach spectrometers to mobile phones and so on. So that's where we're headed on real science education. So I just wanted to give you a couple final thoughts. I've tried to illustrate that knowledge is critical, but the sense of wonder maybe is even more critical when you're trying to encourage people to do science. I've also tried to say that working on complex problems is really not easy. It can be very frustrating, but it can be very rewarding as we try to better our society with projects that can help to better our society. It would be highly fortuitous if we were to be able to create a next generation of sophisticated problem solvers. It would be highly fortuitous if the next generation could tackle these authentic, big picture, difficult problems that need physics and need science to solve. So I'll leave you with the words of one of my favorite artists, Paul Klee. So I said it was fortuitous. He said basically, we must make the fortuitous essential. So it would be great if we could make the fortuitous essential. And we have to keep looking for the better tools. Thank you.